Okay, in Euler's method, having the step size will do approximately what to the error? Double it, have it, or quadruple it? Have it. Double the steps, half the error. There are other numerical methods where doubling the steps actually reduces the error more than having it, but we won't learn them in this class. But in this one, it halves it. All right, true or false? Euler's method gives you an exact solution. False. It's a numerical approximate solution. Having the step size, right? If the step size is smaller, you have to have more steps. Sorry, yeah. Having the step size or doubling the number of steps is the same thing. Yeah. Okay, class 5 was attached to class 4 that I gave you on Friday. So it was in the last packet I gave you. Does anybody not have it? All right, good. All right, so we're going to start with a little discussion of slope. So in general, the formula for slope is change in y over change in x, right? So if I wanted to solve that equation for delta y, I could just multiply both sides by delta x, right? So delta y would be m delta x, m times delta x. All right, so Euler's method is a numerical technique that gives us a precise way to draw a particular solution by following the slope field. So last class we eyeballed it and we tried to just follow the slope field and draw a curve. This is going to make it a little more accurate. Okay, rather than just trying to follow it, we're going to use numbers and have numbers guide how we draw the slopes. So it takes advantage of the fact that the tangent line approximates the solution curve near the point of tangency. So remember linear approximation from Calc 1, right? So each one of these little tangent lines is a linear approximation of the solution. So as long as you don't go too far from the point of tangency, it's a good approximation. So here's an initial value problem, t minus y squared. I've got the slope field drawn here. If y of 0 equals 1, that's my initial condition, so I can draw that in. So this is t, this is y. So y of 0 is 1. I've got an initial condition. And I'm going to try to follow the slope field just by sketching, follow the slopes. And I'm going to sketch a solution that has that initial value. And I'm going to use that sketch to estimate y of a half and y of 2. All right, so if I try to follow the slope field, it looks like it does something like that. Oops. It did something funny up here that I wasn't expecting. Maybe these look like they get a little bit less steep and then steeper. I don't know, it's hard to follow. Do you think I did it? Okay. All right, so if I want to know y of 0.5, right, I just go find 0.5 on the t-axis, I go up to my graph, and I say, looks like y of 0.5 is about 0.8. From my picture, right? And y of 2, go over to my graph, looks like it's, I don't know, I didn't draw that very straight. 1.2. Those are really rough estimates because 1, the curve was an estimate, and 2, I'm going up to the curve and estimating along the y-axis. So those are really, really rough estimates. We're going to use Euler's method to come up with a better way of getting those estimates. It's basically the same thing. We're just going to be more precise about how to draw this curve. So if I wanted to get a better estimate for y of 0.5, I'm going to draw a picture. Okay, so I know the slope at 1, at the point 0, 1. Right? So the slope of the tangent line at my initial condition, right? because I know the slope at any point is t minus y squared. So it's going to be 0 minus 1 squared is -1. So when I'm near the point 0, 1, I can use a line that has a slope of -1 to approximate the curve. Right, my tangent line is going to have slope of -1. So if I draw a line right here that has a slope of -1, that was terrible. Slope of -1 would look like that, something like that. Okay, so there's my tangent line to the curve. And I'm going to use the tangent line instead of the curve to approximate the value at a half, because a half is relatively close to 0, right? Probably a smaller step size would be better, but a half is pretty close to 0. So this is the point I'd like to know, but I'm going to find the point on the line. Okay, so if I had drew a little triangle there, then I know the slope of this line is -1, right? And I know that my change in x is 0.5. Could I solve for that change in y? Yeah, I would just say, okay, well, delta y is my slope times delta x. That's what we did earlier. My slope is -1, and delta x is 0.5. So my change in y is 0.5. Yes, it's, yeah, right, -0.5 because of the -1. Thank you. So my y value started at 1, and this change in y is -0.5, which means that what's the y value of this point right here? 0.5. Yeah, this y value is 1. We go down by a half. That's my change in y. So the y value right here is a half. So this point is approximating this point because we're using a tangent line approximation to approximate the value of the curve. So I'm going to say that y of 0.5 is approximately the old y value, which is 1, plus the change in y that I calculated, which was -0.5, which is 0.5. So it's an approximation of the value of y at 0.5 using a tangent line. Now, if I had used a step size smaller than 0.5, if my delta x, were really tiny, like, 0.1, I probably would have had a much better approximation, right? But the further away you get from the point of tangency, the bigger the error gets. So we're going to use 0.5 for now, but use smaller step size, less error. All right, so we're going to continue doing the same method. Estimate y of 1, y of 1.5, and y of 2. So we have this table set up to help us organize the work. All right, so k is just a counter to tell us what step we're on. So at step 0, right, my t value and my y value are 0 and 1. That's just my initial condition that was given. Y of 0 is 1. And dy dt at this point was -1. We already calculated that. You just plug that into the equation t minus y squared, the differential equation. Delta t, we're going to use a step size of a half for each of these. And then we calculate delta y, right? And delta y, we said, is just slope times delta t. All right, so in this case, the slope times the delta t is -0.5. Okay. Then we use this information to calculate the next point on the curve. So step 1, first calculation, p sub k, my next t value, is going to be my previous t value plus delta t. So that would be 0 plus 0.5, which is 0.5. My next y value is the old y value plus the delta y. 1 plus negative 0.5 is negative 0.5. And then we use my new point, use the new point t comma y to calculate a new slope using the differential equation, t minus dy dt is t minus y squared. So I plug in the t, a half, plug in the y, negative a half. So we have a half minus a quarter is a quarter. Y sub k is positive 0.5, yeah. Yeah. Sorry. So then my dy dt comes out the same because you square a positive or a negative. So I have a half minus a quarter, which is a quarter. Delta t is just going to stay a constant 0.5. Delta t is something that you choose or your textbook tells you what size to use. And then we calculate our new delta y, which is slope times delta t. 0.25 times 0.5 is 0.125. All right, so now we use our delta t and our delta y to calculate new t and y values. So step 2 here, my old t value is 0.5. I'm going to take a step size of 0.5, so I land at 1. My old y value is a half. My delta t is 0.125. I add them and I get 0.625. I plug my new t and y value into dy dt to calculate a new slope. Oh, that's what I meant to add. 0.5 was my old y sub k, and I added 0.125, the change in y. Did I say something different than I did? Okay, sorry. Yeah, delta t is just going to be 0.5 every time. So you don't have to write it in your table if you don't want to. And then I should put a little note. T sub k is always the previous t, so that would be k minus 1 plus delta t. And y sub k is always the previous k, so y sub k minus 1 plus delta y. Okay, so I take my new t comma y, my new point that is an approximation to the point on the curve, and I plug it into the differential equation to get a new slope. So 1 minus 0.625 squared is 0.609375. Delta t, 0.5. Delta y, slope times delta t. So 0.609375 times a half comes out to 0.304687.5. You might notice I'm keeping all the decimal places because Euler's method is already an approximate method. You're already introducing error just by using it. I don't want to introduce more error by rounding all my numbers. All right, so step 3. Calculate a new t and a new y value. The previous t plus delta t, 1 plus a half is 1.5. And 0.625 plus 0.304, blah, 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 comes out to 0.9296875. Previous y plus delta y. So then I take my t value and my y value and I plug into the differential equation to get a new slope. So 1.5 minus 0.929 squared comes out to 0.63568. And I think that had more decimals and I didn't write them down. At some point, you could just store it in your calculator. if you're writing this out for me, like for a quiz or something, you don't have to write down every single decimal, but you should use every single decimal when you're having your calculator do the calculations. Delta t is again 0.5, and delta y is slope times delta t, and this comes out to something like 0.3178 with some other numbers. Okay, finally, step 4. My new t value is my old t value plus delta t. 1.5 plus 1/2 is 2. And this is what I was looking for, right? These are the values I wanted, 1, 1.5, and 2 for t. So I've got those. This is the last one I need. My new y is my old y, 0.929, blah, 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 plus delta y, 0.3178. And that comes out to approximately 1.25. So we have that y of 2 is approximately 1.25. Right? The value from the table of y when t is 2. That is Euler's method. You can choose different step sizes, right? If you make delta t smaller, the method becomes more accurate. Let's look at how this compared 1.25 to our estimate using the slope field. Y of 2, I guessed about 1.2. We would have to solve analytically to know how close we were. With any accuracy. Any questions? If the step size were 0, oh yeah, as you let the step size go to 0, the error goes to 0, and you approach an exact solution. So that's a great thing about a numerical method is we have computers with such computing power, you can make the step size basically as small as you want, and get as accurate as you want. If you have some idea like, I need my solution, I need the value of y of 2 to be accurate to 6 decimal places, there is a way to figure out what your delta t has to be to give you that. We haven't talked about that, but you can be as accurate as you want. As delta t goes to 0, error goes to 0, and you approach the exact solution. All right, so I'm going to have you try some.